recent session is by Qinheping Hu, guarantees in program synthesis.
Hi everyone. Today I'm talking about guarantees in program synthesis. This is a driver with Jason Breck, John Cyphert, Lois D'Antoni, and Tom Breck. Let me first introduce what is the program synthesis. A program synthesizer generally takes as input a specification, which describes the intents of the users, what the users want his programs to do, and a search space which contains all candidate solutions. And the goal of a program synthesizer is to find a program P in the search space such that P satisfies their specifications. However, finding any correct solution is not always enough. Why? Let me show you an example. Say you are synthesizing a Java program which increases the input x by 1 when the input is in the range from 0 to 100. A possible solution will be this: just return x plus 1, which is simple and clean. Another possible solution is a 100 lines lookup table. The user may prefer one solution than the others. However, since the second solution is also correct, the solution 2 is also correct, a program synthesizer may return the solution 2 instead of the solution 1. And the solution 2 may be useless for the user since it's too large. And you may think this is just silly artificial examples, but actually it is a true story. In our PLDS17 papers, we were trying to inverse programs using one of the state-of-the-art synthesizer, CVC4, and we expect the output to be a program like this, a one-line function, simple and clean. However, this is what the CVC4 output for us. It's hard to see, but I can tell you it's a thousands of line lookup table. It's just if something, out something. So my research focused on introducing guarantees into program synthesis to address such problems. For example, I will introduce two types of guarantees in this talk. The first one is quantitative objective, which allow users to prefer some solutions than others. For example, the users can say, I want solutions with smaller size, greater likelihood, or smaller numbers of if-then-else statements in the solutions. And the second type of guarantees I will talk about is to prove unrealizability of synthesis problems, but I will discuss this later. The two contributions in this talk to focus on the domain of synthesis problems, which also called SyGus problems. In SyGus problems, the specification is a logic formula. For example, this logic formula states that we want to find a program P such that P is greater or equal than both input x and y, and it should be either equal to x or equal to y. And it turns out that P is the maximal max2 function compute the maximum of two input. And in SyGus, the search space is described by a grammar, and you can see this grammar produces all linear terms with if-then-else statement operations. And with this example specification and example search space, a synthesizer may find us a program P looks like this, which actually compute the maximum of two inputs. But yeah, our first contribution is introducing quantitative objective to SyGus problem. We call it QSyGus. In QSyGus, the user can specify the quantitative objective. For example, he can say, I want to minimize the number of ITE in the solutions by assigning weight to production rules. Here you can see the users assign weight 1 to the ITE productions and assign weight 0 to all other productions, such that now to find a minimized solutions is equivalent to find the solutions with minimized number of ITE. So to solve the QSyGus problems, what we do is we reduce QSyGus problem to traditional SyGus problems and refine the solution iteratively. The first step is we ignore the weight from the weighted grammar to get a traditional SyGus problems and solve these problems with a off-the-shelf solver. Say a solver finds us a solution look like this, which contains 2 ITE, so the weight of the solution is 2. Now the question is, can we find a better solution? What we do is we construct a grammar named g less than 2, which only accept terms with way less than 2. And you can find how we construct the grammas in our papers, but we just get these grammas. And the next step is to ask the solver, can we find a solution in the gramma g less than 2? If we can find one, we get a better solution. The better solution is if x greater than y, we return x, otherwise we return y, which is indeed a max2 functions. And you can observe that the weight of this function is 1. Now the question is, can we find a better solution? So we construct a gramma only accept way with way 0 containing no if-then-else statement. And it turns out that the solution, the last solution is optimal only if there's no solutions in the gramma g less than 1. This motivates our second guarantees in program synthesis. Can we prove the unrealizability of program synthesis? That is, can we prove there's no solutions in the search space? This problem is challenging because if the search space contains infinite number of candidate solutions, any search-based technique will time out when exhausting the search space. So our second contribution is our CAF 19 works for proving unrealizability for SyGus problems. Let's still use this example to show how we prove unrealizability for SyGus problems. The gramma is just produce linear terms without ITE operations, and we can observe that we don't need to prove there's no solution for the specification. All we need to do is to prove there's no solution even for the following 4 test cases: 0, 0, 0, 1, 1, 0, and 2, 0. What we do is reduce the SyGus problems over the test case to verification problems. So for each non-terminals, we have a function, recursive functions. In the recursive function, we non-deterministically choose a production to apply. Say, if we choose the production 0, we just return all 0, or return all 1 if we choose the production 1. And similarly, we construct the if branch for each production use. And at last, we assert that we cannot fire programs satisfy all test cases. And we prove that if the assertions in the verification is always holds, we know that the original SyGus problem is unrealizable. And we can solve this verification problem by an off-the-shelf verification solver. As a conclusion, we introduced 2 types of guarantees in program synthesis: the quantitative objective and proving unrealizability. For future work, we may explore other quantitative objectives other than the syntactic quantitative objective. For example, we can consider the semantic quantitative objective or the resources-bound synthesis. And one other possibility is to prove in unrealizability problems, synthesis problems beyond SyGus. And yeah, that's my talk. Thank you. Any question? Yeah.
So in the first part where you're trying to reduce the number of if-then-elses you're using, for example, do you always just sort of step down one at a time, or is there can you do some sort of search to accelerate this process? I'm worrying about a case where like your initial solution comes out with 500 if-then-elses, and then you take forever to step down until you realize you can do it with 2.
It depends on what the SyGus solver we use to solve the reduced SyGus problems. But in the paper, we prove that for some kind of problems, it will always terminate in finite number of iterations. But also, we know that there are some kind of problems that it could not terminate in finite number of iterations. But we can still do something like the best effort, try to find a better solution than just using SyGus problem to find non-weighty versions of SyGus problems.
So you said that you only needed to check like 4 examples to make sure that something is unrealizable. How do you come up with what the 4 examples that you need to assert are to pass off to the off-the-shelf verify?
Yes, the test case can come from something like the SyGus loop, the counter example guide synthesis loop. We initialize the example set with empty or just simple 0 examples, and we find a solution for it. If we can find one, we check if the solution is correct by a verifier. If it is incorrect, we find another counter example and we add a new counter example to the example set. And if the solution is correct, we just return it to the users. Or otherwise, we can also use some random generation to generate random input example, which could also be helpful.